Hello everyone! Welcome back to the Secrets of Calculus. Today, we will be combining functions together into sums, scalar multiples, products, and quotients. And this will simplify some of the big brain tools we've been using to calculate derivatives. Oh, hang on. Is this video too long for you? Here's the formulas. Let me know what you did with that extra free time. So for the last couple episodes, we've been finding derivatives of functions like x squared, e to the x, and sine of x, all in an attempt to make this alpine slide more interesting and less dangerous. Although, it seems we now have too many functions in the boardroom, which all need different derivatives in order to keep track of how fast the sled is going at any particular time. The reason I say there's too many is because we have functions like cosecant of x here, which is really just 1 over sine of x. Yet their derivatives have nothing to do with each other? Yeah, we need to fix that. Let's start by first inviting all the polynomials over. So, functions like x squared are kind of boring when they're alone like this. They tend to instead appear like this, like 3x squared plus 2x minus 5. But how would we take this derivative? Let's go back to the limit definition real quick. Now let's suppose a function was 3x squared plus 2x minus 5. Remember that the f of x plus h replaces all the x's with x plus h. And here we invoke the convenience of limits and say that approaching 0 is not the same as equaling 0, so we can divide everything by h. And now we use convenience again to say that approaching is the same as equaling, so we plug in h equals 0. There's a few things to notice here. First of all, this is like if we took the derivative of each part of the sum and then added the derivative. The derivative of 3x squared is interesting because it's 3 times the derivative of x squared, which is why we get a 6x here. And this is not just true for polynomials. Derivatives distribute over addition and subtraction, and you can factor constants out. Neat! Now that we know this, we can tackle functions like x squared times sine of x. What do we do here? Well, let's see what the limit has to say. And now we split the limit and factor out the functions of x as much as we possibly can. There's a lot of limits here. So with some of these limits, we can use convenience to say that h approaching 0 is not the same as saying h equals 0, and that allows us to divide by h to simplify wherever we can. And now we can use convenience again to say, psych, approaching is actually the same as equaling. And that lets us plug in h equals 0 into some of these limits. Now we need to remember back to last episode when we used brute force to find these remaining limits. We found that the limit as h approaches 0 of cosine of h minus 1, all that over h equaled 0, and that the limit as h approaches 0 of sine of h over h equaled 1. And there we go. That is the derivative of x squared times sine of x. Now, notice that the derivative of x squared is 2x, and the derivative of sine of x is cosine of x. This reveals the pattern that defines the derivative product rule for any two functions. The derivative of the product of two functions is the derivative of the first function times the second function left alone, plus the first function left alone times the derivative of the second function. So that's the product rule. The pair that goes along with it is the quotient rule, which is going to be mostly obsolete next episode when we talk about the chain rule. Nonetheless, we'll use the limit definition on two functions divided by each other. This time we'll pick the function x squared divided by e to the x. Now we need to make the denominators equal so we can subtract the fractions. And we can now factor out as many functions of x as possible to split the limit. And you know the drill from here. We now use convenience to say approaching 0 is not the same as equaling 0, so we can simplify, and then say it is the same to plug in the limit. Okay, so this limit is going to be a little tricky. So let's brute force the answer by letting h get really small. This limit looks like it's approaching -1. So when we plug that in, we get this. Now to get it into the form you see in the quotient rule, we can multiply this by a fancy one, specifically e to the x over e to the x. Now, it's hard to tell what's happening with e to the x because it is its own derivative, but I figured the algebra would be easier to follow than if I used sine of x. This reveals what the quotient rule states. If you have trouble memorizing this, try using this trick. Low d high minus high d low over low squared. The d high in this case means the derivative of the numerator, and the d low means the derivative of the denominator. So I mentioned last episode that some of the trig rules are obsolete now that we know the quotient rule. To see why, let's take a look at the derivative of tangent of x. The tangent can be instead written as sine of x over cosine of x. And hey, we know how to take those derivatives. Since we're in a fraction, we can just mindlessly plug them into the quotient rule. So the derivatives of sine of x and cosine of x are based on
the square of j.
It says to turn sine of x into cosine of x and cosine of x into negative sine of x. Now here's a really cool property of trig. Since sine and cosine basically tell you the side lengths of a right triangle if the hypotenuse is 1, we can use Pythagorean theorem to see that sine squared plus cosine squared of x equals 1. So we're left with 1 over cosine squared of x. And since 1 over cosine of x equals secant of x, the derivative of tangent of x is secant squared of x. That's 2 of the 3 major big brain derivative tricks down. The third one is called the chain rule, which actually is going to be covered in 2 videos. See you next time!